visit Galileo House, and we will have a little welcome drink in this place. We will meet here at 5 in front of this room, and we walk to Galileo's house, which is quite close to the department. Okay? And now we can start with the lecture. We have the first lecture of Jian Qiu, and he's going to talk about localization of 5D superimpedance. Please.
Thank you for the invitation. So the goal of these 3 lectures is quite modest. I'm just going to walk you through a calculation of 5-dimensional super-young mills of about 5D Sasaki Einstein manifolds. And by some, I actually meant pretty much this S5. But along the way, I'll treat some of the subject with sufficient generality such that in the end, you have enough to also compute a special class of Sasaki Einstein manifolds, which is called the YTQ manifold. But this will be my working example. So I'll divide my lecture into 3 parts. So first of all is just the setup. And I'll start from just looking at flat 5D super-young mills. And then I'll put it onto, I'll move on to curved space. And then this will lead to some small sub-subjects, which is mainly Killian spinors, as well as Sasaki Einstein manifold. So I'll try to make this part not too big of a digression, because I do want to get to the results as fast as I can. And then the second part will be just the actual localization. So I'll just give you the general story of how localization goes. And then there will be something that we need to do, which is, roughly speaking, a change of variable for our fields. Variable. It is also sometimes called twisting, but I prefer to call it just change of variable. And then after that, we will have to deal with localization locus. This would lead to what's known as the contact instantons. Which are other new objects, and I would like to touch on this slightly. And finally, I will compare our results with the flat space, perturbation calculation. So, and then once this is done, which is already quite a project, I'll go back to the third. I try to reach the third part, which is number 3. The big 3 is I'll go back to talk about Sasaki Einstein manifolds in more systematic ways, and then I'll tell you how to construct this manifold, YTQ space, and hopefully you will have a clue of how to do computation for this space, and then, well, maybe I just quote the result for this space. So this is the plan for the talk. So let me start with the first part, the setup. I'll start from flat space. Whoops. I'll start from the flat space super-young mills. Let me just forestall a question, namely, in which signature am I working in? I will leave it unspecified. because I don't want to get into this discussion. Okay. First of all, flat space, sweeping wheels, n equal to 1. I'll just analytically continue back and forth between the Lorentzian and Euclidean signatures, pretending that there's no, pretending there's no problem.
There is no problem.
Oh, good.
Yeah. People who are concerned about that there might be a problem usually make the following error of assuming that fermions are supposed to have a real structure.
Okay.
But that's a misconception, because actually the Bayes integral for fermions is an algebraic operation. The integral d psi of psi is 1.
Okay.
In discussing that operation, you never mention the psi bar.
Right.
So a typical theory in which there is no real structure for fermions in Euclidean signature is the standard model of particle physics.
Okay. Oh, well, that, okay.
In general, 2 points. One is if there's, in general, there's no problem associated with fermions in Euclidean signature.
Okay.
After all, people study the standard model by computer.
Yeah. So anyway, so this is good, and
so don't describe it by saying you're pretending that there is no problem.
Thank you. This is quite reassuring.
A sharper statement is that there's no issue that's special to this problem. If a question is raised, just ask the person who raises it how he or she understands the standard model.
Yeah, okay, I'll remember that. Okay, so let me, where is it? So the field content is, well, it's the fields. So this means H supercharge. Fields are the gauge field, a fermion, and then a real scalar all in the adjoint, of course. And then this fermion, it's actually neither Majorana or, well, it doesn't make sense to talk about Lyell here. It's actually what's known as the, so this is called symplectic Majorana. Then it satisfies the following equation, constraints rather, namely the complex conjugate of this is equal to B epsilon. Let me write it down. So let me explain the notation. So B is the charge conjugation matrix. B is defined. So gamma mu is equal to that. And then there's a, let me just say that there's another matrix which is also called, I think it's also called charge conjugation, but it's defined as transpose. I think both are called charge conjugation matrix. And in the Euclidean signature, these two will be the same. And then in the Lorentzian signature, they will differ by gamma 0, assuming that 0 is the guy with the negative signature.
Well, part of what I told you was that you shouldn't discuss lambda star.
But this is just how, I mean,
in Euclidean signature, you never discuss lambda star. If someone asks you a question about Lorentz signature, in Lorentz signature, fermions are real. And a discussion of lambda star will be part of that. But in Euclidean signature, it's irrelevant whether fermions have a real structure. You never discuss it. There are objects lambda and Lagrangian, and you should never talk about lambda star.
Right. In actually writing the Lagrangian, I will never need this star.
Okay.
So which means we have no problem in defining the integral. Okay. So so this is anyway.
You also don't need it in the Euclidean Lorentz signature, except that in Lorentz signature, someone can ask you if your Lagrangian is permission.
Yeah.
And that's when you would write down this formula.
Okay.
But you can keep this formula in Euclidean signature if you think as a reduction for example, R5,1 signature, for example, you have means just to reduce down.
After you've reduced, you would never use that formula.
Right, but you will just get your own sign for kinetic term for the scalar, but you can keep this relative conditions for fermions.
Reality conditions for fermions in Euclidean signature are usually wrong. They're just not part of Euclidean signature formula.
The standard model is a typical example. Another typical example is actually the Rocek string theory.
Right, but
All our favorite theories, more or less, the first approximation, all our favorite theories have the property that Euclidean and interferometers don't have a real structure.
Okay, this,
So
anyway.
it's unlikely in the Euclidean space discussion that you should write a formula that contains lambda star.
Anyway, so as I was saying that for the action on the supersymmetry transformation, I will not need anything related. I mean, I will not have this complex conjugation. So I think it's fine. I mean, as far as the path integral is concerned. Just a matter of notation, since I'll be forming, so to take two spinors, I'll form their invariants by taking complex conjugates and then multiplying by this charge conjugation matrix, and then multiply by the second spinor. This is an invariant, but for notational convenience, I will just always write it as this.
That's not just notational convenience, that's just closer to the right point, like I keep telling you.
Well, here it's
That's okay, that's you right there.
Yeah.
I'm fluent. So your formula for the transpose is fine. That's also a good way to write it.
Yeah, oh, okay. So this is just notation. Okay. Now, so this is in 5D. To get better grip of the structure of the theory, let's compactify in one dimension and go back down to 4D, because there the n equal to 1 actually turns into n equal to 2 in 4D language, and we have we can describe the theory using the n equal to 1 superfield there, and which can express things in a very compact way. So let's go back to 4D. So you compactify in a circle. And then in 4 dimension, the theory can be described. Let's just talk about diagonal with described by the following fields. When you call it curly A and W A R. So this curly A is not the same as the gauge field, but it's somehow standard notation. This is a chiral superfield. And then this is also chiral, but so A is the adjoint index, alpha is the spinor index. And then I'll also need an F, which is a holomorphic function of A. This is the free potential. Critical 10. Sure. So what happens when you go back to 4D, when you compactify down to 4D, is that the fixed components of the gauge field combines with this field, making it a complex scalar, which is the leading component of this guy. So the leading component of this guy, it's basically, roughly speaking, A5. And then the second, the next component of this superfield is the half of the genome, half of this guy. And then the next one, of course, is the auxiliary field. And then for this W, its leading component is the other half of this A genome. And then this combination, this is the polarity derivative in superspace. This gives you the self-loop part of the field strength, and then the antisymmetric combination will give you auxiliary field. But so this is how you will be describing the theory in 4 dimensions. So sorry, when you compactify to 4 dimensions, and then the action is written in a very compact way. It is just given by so it's given by 2 parts. Basically, this part is it comes with a chiral integral, and then this will be responsible for the gauge field kinetic energy. And this part will give you the kinetic energy for the scalar field. So, as an example, so in the 4D case, as an example, f can be chosen as, this is the standard case, f can be chosen as over 2 pi plus 1 pi g minus squared. So summation. So this is the classical part. And then with this f, if you plug it in here and here, what you will get is the following. This will lead to the term, the usual term, and so with this choice, what you get for the gauge field, for the field strength is these two combinations, namely the kinetic part for the gauge field as well as the theta angle term. Okay, so now we're in 5D. The story actually kind of simplifies somewhat. It can be shown that the most general f is of the form. So, well, of course, so you can also add a linear term and a constant term. But these two will not show itself in the action because, well, since f always appears with derivative, and also here, and also the linear term will not appear because here it's a full integral over full superspace. So these two terms, I can just erase them. They will not matter. So let us just try to understand at least in one of the possible ways why that there is only a squared and a cubed term. Okay. So we already know what a squared term is going to be because we have seen it from here. And then let's just look at an a cubed term inside of the pre-potential. That's going to lead to the following terms. So an a cubed term in the pre-potential is going to give us two, for the gauge part, it's going to give us the Chern-Simons term plus the kinetic energy of the gauge field, but with the field dependent coupling. So to see this roughly, you just focus on this term here. Namely, you take second derivative against this cubic term, you end up with just 1a, and then you can just identify this. And then remember that the leading component of A is basically I sigma plus A5. And then you can identify A5 with this one and I sigma with this one. And then the sigma term, since it's identified with Young's coupling, so it shows up here as a field-dependent coupling, while the A5 term will lead to something like A5 times f by f, which is one part of the Chern-Simons term. And if you do things carefully, you'll get the full Chern-Simons term.
Can you just set me straight? What part of the backboard is 4-dimensional and what's 5-dimensional?
Here I'm back to 5 now.
But you were pointing at the 4-dimensional action.
Right, so you can, I'm just saying that the way that you can get this term is to take an analogy from the 4-dimensional calculation.
Okay.
Yeah, okay. So any other questions so far?
But in 5 dimensions, we could have a term that would break conformal rings from the AA. It would have to be real. So you couldn't have a thing in it. But you could have the other part.
Well, I mean, so 5 dimensions, if you have a term like this, in the end, in the Lagrangian, you will get a term like this. So theta, kappa, sorry.
No, nothing.
So-
No energies.
Right, in flat space, this is forbidden. But in the curved space, when you have a compact structure, this term will lead you to a term like theta, kappa, f wedge f, and then you can write it sort of suggestively as.
No, I wasn't talking about that term. In flat space, you can have the 1 over g squared. In flat space.
Right, yeah, yes you can. But this one will lead to something like so in 5D this is a conserved current. So this is like a coupling the conserved current with a background connection. I don't understand what this means, but this is just one way of understanding what happens to this theta term. So any other questions? Okay, so now it's important that this A cubed term is going to lead us to a Chern-Simons term, and whose coupling has to be quantized on the grounds of gauge invariance. And hence, let's ask, what if in the pre-potential we have an A force term, and that is going to just lead to something like sigma CS5. So field dependent coupling for the Chern-Simons term, but that's never going to be quantized. So it's ruled out because of gauge invariance. So
No, it's not invariant under local gauge transformation, under small gauge transformations either.
large gauge transformation.
Oh, it's also not invariant under small ones, because CS changes by total derivative.
Okay.
Multiply sigma won't be gauge invariant.
Oh, okay. Well, okay. So it's ruled out that gauge invariance. Okay. So now, so this is the most general story, and let me just make a remark that if you start out with just the A square term, namely without A cube, and then the A cube term will be generated. So let me write the. Somehow I'll write it C and D. Well, okay. So C will be something like this. So this cube term will be generated at one loop, and only at one loop. The way to see it is the following. This C, remember that is the Amils coupling, so it carries dimension in 5 dimensions. While D here, if you count the dimension, it's a dimensionless coefficient, and it has. If this is generated, it cannot depend on coupling. So it must be a one loop effect, because in one loop, what you do is that you compute the determinant, which is independent of the coupling. So, and we will, in the end, once we have obtained our results for the localization, we will also go back to compute in flat space just to see what this coefficient is, and compare that with the localization result, and then of course we'll get a match as a check that we're still on the right track. And so far, I think let's see. Yeah, okay. So that's all I want to say about flat space super Yang-Mills. And any questions before I erase all of this stuff? So next I will move on to curved space.
Actually, I have one question. So you said you can only generate this at one loop, but so why can't? But at higher loops, you think that it could be multiplied by vertices.
Right, but those will be.
So when you just throw in the value, you're saying they're not there.
I would imagine that those were just. The honest answer is I don't know, because I never done any two-loop calculation. But since based on dimension grounds, the coefficient cannot depend on the
No,
coupling.
but I'm saying you can have a G squared times lambda vector, where lambda is the current.
G squared times lambda.
Yeah, the lambda is some cutoff. That's dimensionals.
Okay, for that, I don't know. I never done any two-loop calculation. I mean, I did it to one loop and.
But when you say it as one loop, to generate a one loop, you need massive fields you're integrating out.
Right.
I'm not sure what you have in mind.
So what I have in mind is that I will compute. The only scale that I have in the theory when I will do the background field computation, and then the only background field is the non-zero sigma.
Everything was clear except the following. What are the massive fields you integrated out to get that term?
So okay, what I will do is I'll do things in Coulomb branch, and then I'll give an expectation value to this field sigma.
Again, I didn't ask how you do the calculation. You're not claiming to get it just from the angles multiple, I don't think. Because that's a parity conserving theory, which wouldn't generate.
Right, I'll add all the matches and everything.
So you'll have some massive matter coupled to this.
Right. Okay, any other questions before I move on to curved space? So for curved space, what we'll do is that we'll focus on the a squared term in the potential, because that's the only term that it's not conformal invariant. So the strategy is following. We will start from the flat space, and then we'll couple it to the minimums of 5D supergravity, and then we'll freeze this gravity multiplet and turning off all the fermions, and then figuring out what are the possible backgrounds which would allow you to turn off these fermions. And so let me just first write down the action, which I haven't written down yet. This is still in flat space. And here, this is only for the a squared term. I did not include the cube term. Again, let me remind you that here actually there is a transposition plus a conjugation, but I'm always using this notation. So this is the action. Now let's look at what are conserved currents. You have at least the following. So you have the energy momentum tensor, you have the supercurrent, and you have the SU2 current. SU2 current related to the rotation of this index. Now, so you couple these currents to the minimal supergravity multiplet, which would contain actually more than, so this one will be coupled to the metric, and this one to the gravitino, and this one to its own gauge field. But the minimal supergravity multiplet contains more fields. Let me just give you a list of the fields there, because some of these fields will feature in the Killing-Skinner equation. So I think it's necessary to write it down. This is the minimal. And also, I must say that I'm no expert in supergravity, so if I start preaching heresy, let me know. So you have the field line, and then gravitino. So these are all, oh, there's one more, sorry. So these are all the fields in the minimal supergravity multiplets. We have the traditional, the field line, the gravitino, graviphoton, and then there are some scalars. One scalar is an isotriplet, so it contains two indices. And then there's another scalar which is singlet, and they have an extra spinner, which is also an isodoublet, plus the gauge field for the SU2 gauge field, for the SU2 gauge field. So now our goal is that, as I said, for these bosonic fields, the field line, these guys, I want to freeze them to a desired value. This can be done provided, so freeze backgrounds. This is okay provided that this, what's the notation? Is 0, and as well as this is 0. Now, which means we have to look at what's the right-hand side of these supersymmetry variations. Let me just write it down. This is going to lead to the Killing spinner. So it's a bit long. Okay, so, and then delta pi is equal to I'm going to write it. So let's just look at the right-hand side of the SUSY variation of the gravitino. Basically, almost all of the backgrounds, both bosonic fields, will feature in this in the right-hand side of this variation. And then the reason I didn't write this down is because I'm not going to consider the most general background, just a very special case. And if you wonder what this should be, just to look at, this is from Druka's paper. So just check this out in that paper. And so I'm going to go to a very specific background, which is I'll choose so this is the background. Basically, everybody is going to be set to 0 except this this scalar, which is an isotriplet. And then, and also without loss of generality, assume that it's proportional to sigma 3. Okay, so now it can be shown that with this choice of background, this vanishes completely. So let's just worry about what's the right-hand side of the gravitino. Oh gosh. Oh, my voice didn't hold up. So we set B, A, and A SU2 to 0. So this is gone. All of these are gone. So we're just left with this simple equation. So let's rewrite it over there. So the condition for the vanishing of the variation of the gravitino is that so this has to be 0, and then since we assume that sigma is proportional to sigma, t is proportional to sigma 3, so we just get this equation. So the equation we need to solve is plus or minus some number times gamma n. So this is the Killing spinor equation that we need to solve. Here the number is unspecified yet. Now, what we will do next is that basically we try to exploit this equation as much as we can, derive what geometrical properties the manifold must have. So, for example, one thing we can immediately get is the following. This would immediately tell you that the manifold is Einstein. So let me just show you how to get this. Well, it's actually quite simple. We just apply another d on both sides and then use the Killing equation again, which you will get. So let me call this x more professional. Okay. So you just apply another dn on both sides and then use the Killing equation again. You just get this equation. And then let's look at what if I take the antisymmetric product, antisymmetric combination of the two indices. On the left side, I'll just get the curvature term. And okay, later. Again, sorry, I have to interrupt myself and give you some notation. Namely, I'll write gamma P1 Pk. This is just the totally anti-symmetrized product of gamma P1, gamma Pk. And also in 5 dimension, if you have five of these guys, the right it's just going to be an epsilon symbol. But if you have 3 of these guys, P, Q, R, it's going to be equivalent to P, Q, R, S, T, gamma, S, T. So this is specific. This is for 5. And so. Okay, so this is the equation you get by taking the antisymmetric combination. Now, what you do next is that you multiply both sides again by gamma n. And then you have these 3 gamma matrices. You can take a symmetric combination or a totally antisymmetric combination or partially symmetrized combination. And in fact, the totally antisymmetrized combination will vanish thanks to the fact that if you totally antisymmetrize these 3 indices, you can get 0 for the Riemann tensor. So out of these, I'll just get a partially symmetrized combination. And here you can just do some basic gamma matrix algebra. What you will get is number 2 is okay, and which means that okay, so from this you can just imply that you have this, and since this is a number, this equation says that your manifold is Einstein, because that's the Einstein equation. And then here this number is Einstein, but I will specify x to yes. are specified to this number. And then the reason for this is because, I need to ensure that this equation has a solution. And then I know that if I choose this number, it will have a solution, and we'll see this later. Because actually, what we are adding toward is that we have not only Einstein manifold, but also society manifold. So this number will be specific for society manifold. We'll see this in a minute. Any questions? So, what can we do to exploit? Now I changed this. What more can we do to extract information from this equation? So let me just. The strategy is following. Construct out of the solution to this equation some geometrical quantities and deduce what sort of differential equation those quantities satisfy by using the Killing equation over and over again. And then just by looking at those differential equations, you can actually gather an incredible amount of information of your geometry. And in fact, just by knowing that you have a pair of solutions to this equation, a pair by a pair, like one with plus and one with minus, and then so when you have such a pair, it's called 1, 1. You say that you have 1, 1 supersymmetry. So for the full n equal to 1 simple algebra, what you will have is 4, 4, so 4 pairs of 4 plus and 4 minus. But this turns out to be only possible for S5, and in general, this is the best we can do. Okay, so let me first, again, inevitably you have to involve some kind of fields rearrangement. Let me just write it down, and I'm not going to actually show you how to do fields. It's a sheer rhetoric. So this is the for 5 dimension. So this is the fields. So here I'm assuming that every spinner is a baronic, so you insert appropriate signs whenever you have fermionic spinners. Okay. We can define the following quantities. Well, first of all, let me make a remark that by using the Killing, okay, so I have. So by using the Killing equation, you can see that this invariant combination has constant norm, which means you might as well assume that it's equal to 1. That's just a normalization. Now after that, you can define the following. So again, by using the fields rearrangement, you can show that this is equal to 1. In fact, for this, it's simple enough. You can do it yourself using this formula. And also the following relation, that R is Killing. What else can you deduce? So Killing means that E and R, and this is equal to 0. And if I use the metric lower one index, so G, if I call kappa equal to G times R lower one index, this is a one form. Of course, it satisfies the following. So now R kappa is equal to 1, and then now R. And okay, I'm not there yet, sorry. So let me just tell you, this R will be known as the read vector field, and then this kappa is the contact of one form. And then, so let's go further. Let's go further with playing this game. We can define the following object. I'm not going to show you how to do the fields. It's just too much. So I'm going to define further. So this is an anti-symmetric two-form, and it satisfies the following property, namely, it is horizontal with respect to the read vector field, and also for tensors like this, I will raise and lower the index without telling you. That's only the mathematicians who care about this. So again, this follows from field identity. So what it means is the following. Well, it's squares to almost minus 1 plus something. So let me just draw the picture. I think I'll get to the word Sergei and I'll stop here. So let me show the picture. So you have a 5 manifold. You have a vector field R, which is nowhere vanishing since it's got constant length. And then on the transverse plane, you have and so from this, J can be restricted to the plane which is perpendicular to the reed. So on this plane, I have a J acting. And then the fact that this squares to minus G plus this is basically the projector, if you wish, projector to the transverse plane. So this just says that J is the complex structure for the horizontal plane. Or let me just write it like this. So the horizontal plane is also the kernel for the kappa, which is you lower the index for one of the read. So
I'm sorry, is integrability obvious?
sorry.
Is integrability obvious?
No. Well, yeah. In a minute. Actually, I will show in a minute that actually this is not only integral, but it's actually scalar. And besides, let me just. It seems to me that because this is, this is just complex structure for the subbundle, which is defined by the kernel of one form. And I think for general vector bundles, you say something being a complex structure. If you ask if it's integral, it's not meaningful because only for a vector, only for tangent bundles can you describe sort of the Lie bracket and stuff. So far it's just an automorphism square root to minus 1 on this transverse plane. Okay. Again, you just use the K-Skinner equations. You can derive the following equation. So it tells you how this complex structure reacts to the Lagrange-Beta connection. It's given by this. So this doesn't seem to tell us much, but in fact, this condition is what's known as the Satati condition. So let me try to tell you how to read this condition. There are two ways to read this condition. One is that you take a 5 manifold and you call this is my 5 manifold and 5. You consider its metric cone in this way. So namely, the metric cone is defined as follows. you have a big matrix for this, which is equal to PR squared plus R squared G. So G is the matrix for this M5, and then the whole matrix is this, and then it's of a cone shape because as you approach the tip, this part shrinks away, and always remove the tip. So we have a 5-manifold here, so the cone is 6-dimensional. And then this condition, what does this condition say? This condition says that, well, first of all, yeah, okay. Now you have, you can define a new complex structure. Okay, I need a bigger picture. Okay. So that this direction be the R direction, so this direction, and then you have the read direction. This is R, and then you have the further transverse direction. So now we have this J, which is the complex structure acting on this transverse direction, and then you can also define a bigger complex structure which rotates this R direction into this read direction, and altogether they form a complex structure for this cone. So let me just call it. So this guy is basically something like, how should I write it? Small j plus r tensor kappa minus kappa tensor r. So the J tilde is made up of this original J plus this part tells you that it rotates this one into this one into minus that one. Okay, so now if you wonder what property does this guy have, actually this guy, so if this condition is satisfied, you can show that this exactly means this one is covariantly constant. And that means that actually on this cone, you have a scalar. So this cone is scalar. With J, and then its symplectic form is omega is d r squared. I think it's kappa. So with this symplectic structure and complex structure, this cone is a scalar manifold. So this is one way of reading this condition. Another way of reading it is the following. Now, you just locally look at this transverse plane, and then, well, okay, let's erase that. And then this condition will actually tell you that if you just locally look at this transverse plane, this J is locally scalar, because there's no such thing as the transverse manifold, so you can't say that it's complex, it's a scalar manifold, but locally this tells you that J is covariantly constant with respect to the metric, to the big metric restricted to the transverse plane. So the picture is really, I have a cone which is scalar, and I have an R direction, and then also on the transverse direction, I have another scalar structure. In fact, right, and in fact, if you know that your original manifold is Einstein, this transverse scalar structure is scalar Einstein. So okay, so namely, if R is scalar Einstein with this property, so this 4 comes from 16x squared, then on the transverse part, you have, how should I write it? Ij is equal to 6 GI-J. So you have this multiple layer of scalar structures. So I have, how much time do I have?
We have about 5 minutes.
5 minutes, okay. So which means that in the framework we're considering, basically we're just stuck with Sasaki-Einstein manifolds. And so next what I'll do is maybe to give you an example, yes, I think a good example should fill up the time. Any questions so far? So the example is just the simplest subtitanic manifold. It is the fine sphere, and as far as actually it can be presented as the following way. As a U1 vibration over CP2. And then the read direction, the one I call R, is actually the U1 along the fiber. So it's obviously free, and it's free. And then so let's to make this. In fact, the metric of the standard round metric of S5 is already the subtitanic metric. You can check that this condition is satisfied by just doing something on tensor calculation. And right, okay, let's see the next page. So I'll write S5 in this. So I want to choose coordinates adapted to this picture of vibration. So for this purpose, I will first write. This is the equation for S5, and then I'm going to change variable to the following. So this is the same thing as that, so I'll be right. Now you can see one feature is that if you vary theta, it varies the phase of simultaneous the phase of zeta 1, 2, and 3. So you can actually the theta is exactly the coordinate along this fiber. Now with the standard metric for S5, and you can plug in this change of variable, you'll get the pullback metric, which is written in the following way. Let me call this thing. Let me call K equal to. So K is this combination. Oh, by the way, this metric is locally valid, namely it is only valid for Z3 not equal to 0. So this patch covers 1/3 of CP2, and for the other patches you just do similar things, and then you can work out what is the change of variable for theta size, which is quite simple. So the metric is given explicitly adapted to this vibration picture. So you can see that one part of it is just the metric for the fiber, and this part is the metric for the base. CP2 with the standard Fubini-Studi metric. I'm not sure if it's an I or Y. Maybe it's Y. Okay, and then so A is written as DO, so AI is DI. So it's indeed, well, we know that this is a Taylor manifold with the Fubini-Studi metric, and then log of K is the explicit Taylor potential. And then this connection can be thought of as the connection for this U1 bundle. Okay, so now this is a very special case of subtitanic manifold, namely the read. If you look at the obvious of the read vector field, it's closed everywhere, which means you can take S5 and well, you can make quotients along the read direction, you'll get an enormous manifold. But this is almost never going to be the case in general. So in general, best you can hope is that if you take when you just write it schematically, mod it out against the read, what you get in the best case is it's an arbor and usually the read orbit is not closed anywhere except for a few points, which means you can't even take the quotient. So I think this will be a point for me to stop. So any questions?
Questions? If there are no questions, let's thank the speaker again. We will make a meeting half an hour.